Hello, everybody. Mr. Hennon here, and this is another edition of our Chapter 5 Plus notes. This is another application of uniform circular motion. This time, I'm going to kind of be looking at banked curves. In other words, when you are driving down a road and you turn from one road onto another, those aren't really, those are banked. Those are flat. So my first one, we know that if I'm leaving my subdivision and I drive out and I turn, I'm going to need to have, so if I just go around a curve like this, I'm going to need there to be some kind of force toward the center of this curve to allow me to make that curve. And if it's flat or unbanked, that's just going to be happening because of friction. However, what if it's not actually flat? So if I'm driving down the interstate, for example, I'm going at a much higher rate of speed. So usually there, what we do is we actually bank the curve. And for this, we have to start thinking of that geometry. So here's a picture. I like this picture right here, A. It's showing kind of the back end of a banked curve. So if you were to cut it off and kind of look at it, it's going to be banked at a particular angle. So this is the angle that it's actually banked at. And so as the car is traveling in this direction to go around that curve, what we have is we still have a radius of that curve. It's still going to be part of a circle, so we'll have that. In this particular case, what's going to happen is the centripetal force, a portion of it is going to be provided by the horizontal component of the normal force. So we're going to have to do that. Also, to make this a little bit easier, we're going to assume that it's frictionless for right now. I know that seems kind of silly, but if you ever look at exit ramps, for example, and they have a sign up there that says maximum speed 35 miles per hour for that exit ramp, but you come off the interstate going 65, you can still negotiate, you can still make that curve going like 50 miles per hour. And the reason why is they are using the worst case scenario. They're going to use situations where friction is very minimal, or in other words, it's an icy situation or a wet situation, so we could actually ignore it. So that's what we're going to be looking at here. The other part that's interesting is the vertical component of that normal force is actually going to balance the car's weight. So this picture over here is a little bit different than we had before. When we have an object on an incline before, this was not part of a curve. This was just an object sitting on an incline. We had gravity acting down, so this was still our F force of gravity, and we had the normal force like this, which is still pictured over here. What we did before is we broke these apart and we found the perpendicular force and the parallel force. But that was for an object sitting on an incline or sliding down an incline or sliding on an incline. Now we're looking at this car traveling along, and because it's traveling along, there has to be some kind of centripetal force. So there has to be a centripetal force that's going to hold this into a curve. Now, centripetal force is actually a net force, so it's not another force you're adding to it. It's going to be caused by something else. So instead of taking the weight and splitting it up, what we actually find is the normal force is going to increase. So the normal force, if you notice this picture here, this normal force is large enough that it's not the component of the weight that's actually balancing it. Instead, it is a component of that normal force that balances it. So this force is going to balance my weight, and then this is going to provide my centripetal force. So this is actually going to be my centripetal force. So that's what we have to do, is we have to kind of set those up. My centripetal force, for example, here is going to equal the normal force times the sine of the angle, and then the way we find centripetal force is this mv squared over r. And then the normal force times the cosine of the angle. So the angle of this incline here would be the same as the angle between this normal force and straight up. Because if I think about it as it tips, that normal force starts out here and it's tipping away by that same amount. And that's going to equal the weight of the object. You go, okay, why does that matter? Well, the problem is we don't know what the normal force is. There is no good way to measure it unless you're going to put some kind of like scale on that object or on that incline to figure that out. We don't know it. So we're trying to get rid of that concept. So the great way is I can actually take these two equations and I can divide them. So if I divide the left side here, what I end up is the normal force will cancel, and I just end up with sine divided by cosine. Well, sine divided by cosine is tangent. So there we go. Over here, I got mv squared over r, that's my centripetal force equation, over mg, that's the force of gravity or the weight of the object. Notice again, just like when we did with friction on an unbanked curve, the mass of the object is going to cancel. Now I say that, that's a matter of, it doesn't matter how much mass you have to go around a banked curve, you can still make it for this particular setup. But keep in mind that if you're on a banked curve or even on a flat curve, there is a possibility that you might tip over. And so you see those signs about semis tipping over or SUVs tipping over because they're going too fast. That's a different situation. That's not, we're ignoring that. We're going to get to that a little bit when we get into rotational motion. We'll talk about tipping and that idea. So basically this G is in the denominator as well as the R, and you end up with this little equation. I sometimes will take this RG and bring it over to the other side and write this as V equals the square root of RG times the tangent of theta. And the reason I do that is that's very similar when we had our friction equation, that it was the square root of R mu S times G. So we had the rug equation here when we are talking about friction. Now, basically what's happening is in place of that coefficient of friction, the tangent is taken into effect, and we've got it. We're not going to actually do anything where we do both, where we have friction and the bank help us out, but there is a combination of these two equations you could create. We're just not going to go into that. It's just not necessary. These special cases work just fine for us. So this is our new equation here. Let's see what we can do with it. So let's say I look at the Daytona 500. The Daytona 500 is a 2.5 mile track, and you have to travel around it enough that you go 500 miles. So if you notice in this picture, the curves are banked so that those race cars can go zipping around. And you would probably want to make them so that you could ignore friction, or maybe there's oil on the roadway, whatever. And so the maximum radius of a particular curve on that Daytona is 316 meters. That means if I were to kind of follow this along and kind of go from there to the center of the track. I know the track is not a true circle, but the center of that particular curve, that would be about 316 meters, and they're banked at 31 degrees. So if I imagine that if I looked at this car, for example, basically what they're saying is the angle that it's banked at is 31 degrees. If we did that, what's the maximum V they could make it around? So for this, we've got our nice little V equal the square root of RG tangent of theta. We just have to plug in our information. We've got the radius of the curve. So that's going to be our 316 meters. We've got gravity. That's our 9.8 meters per second squared. Notice that it does depend on what gravity is. And then the tangent of the angle here, this 31 degrees, we could chunk everything out. Make sure you are in degree mode on your calculator. Otherwise, you're going to end up with funny answers here. So if I'm going to end this, but I'm going to keep these annotations. Let's pull up a nice little calculator here so we can see how that you get that lovely answer. I am in, let's see, let's get my trig functions here. So let's go ahead and let's take the tangent of 31. Oops, 31 tangent. There's that number, so 0.6 approximately, and then we'll multiply it by 9.8, and we're going to multiply that by 316, and I get this answer, so about 1860.7, and then I want to square root that answer. So let's see if I can square root that answer. It looks like they did it, and I get about 43.13, or about 43 meters per second here. 43 meters per second is somewhere close to around 90 miles per hour, 95 miles per hour. So obviously with friction, these cars can go much faster around these curves. This is kind of the maximum speed if they were frictionless. So that's what I was dealing with, but we could actually go faster. So that's a little bit on the geometry of banked curves. I'm going to throw this into a nice little Google form, take a look at it, and see what you can kind of come up with and answer those questions. We'll work on some problems with them later. Take care.